Welcome to Geo 120. My name's Ed. I'm one of the lecturers in this course. By now you've probably seen Marissa's introductory lecture to the course. She's going to be coordinating the course, so if you have any questions about the logistics or the structure of the course or any of the background kind of things, you can contact Marissa. But if you have any questions about the content that I present, then you can contact me. And all my contact details are in the unit guide that Marissa introduced in her first introductory lecture for the course. So we're going to start off by talking about the geology of Australia. I'm going to give you 2 lectures on the geology of Australia, and we're going to go through from old Australia through to young Australia. So today's lecture is really the first 4 billion year history of our continent, and in the next lecture I'll talk about the more recent 500 million years of our continent. So this really sets the scene for some of the things that we talk about in this unit, and you can get a little bit of an idea about some of the more kind of practical aspects of the theory that you learned in this unit. So Australia is a very old continent. We have minerals going all the way back to 4.4 billion years ago through to the present day. So we've got a huge amount of geological history in this country. It's a really interesting place to do geology. We've got a really diverse range of different rock types here. We've got a diverse range of ages of rock types here. And we've also got an interesting history from a perspective of geologists who've worked within this country. There's been a lot of major discoveries in geology that have come out of people who've worked within our country. So we have things like the oldest minerals, some of the oldest crust, we have some of the oldest evidence of life, we have some of the oldest evidence of multicellular life, we've got indications of things like the snowball earth. All of these are discoveries that have come out of geology that's been done in Australia. So it's a really interesting sort of country to be working within. The continent comprises of many fragments of ancient crust that have been amalgamated over geological time. I think if we think of Australia, we all think of the modern sort of coastline, but Australia hasn't looked like that throughout its entire history. Australia has been built up slowly, and that's what this lecture, these next 2 lectures, is really about, the way that Australia has been built up over geological time. The continent forms part of the Australia tectonic plate, and I'll show you the boundaries of that plate. We think of Australia as being within plate and being very stable. The country itself, the continental Australia, is actually a very stable part of a tectonic plate, of this Australia plate. But there are active boundaries around that plate. We have subduction and collision going on up in the north, and we have fast spreading ridges going on down to the south of the mainland. Australia is actually the fastest moving tectonic plate on the modern Earth. We're moving northwards at about 7 centimetres per year, and we're starting the collision process with Papua New Guinea and Indonesia at the moment. So there's the start of active mountain building going on to the north of Australia as the result of our plate moving northwards. Australia is one of the most seismically active intraplate regions on the Earth. When we think about earthquakes, we're often thinking about plate boundaries. So you think about places like the Pacific Ring of Fire, or the earthquakes that go on in places like Japan or around California. Australia doesn't really have as much seismicity as those places, but considering we're actually sitting more or less in the centre of a tectonic plate, we are quite active for that location. So we're considered the most seismically active intraplate region on the Earth. Here's a picture of Australia's tectonic plate. So this is the boundary that we all think about when we think about Australia. This is really our coastal sort of boundary, around like this, and Tasmania down the bottom here. But our plate is significantly bigger than the outline of the country itself. So this is the boundary of our plate around here, this dark black line. It's going right around the ocean around here. So this is the Australia tectonic plate. There's some arrows that you can see on this diagram. The green arrows are indicating areas where there's active subduction going on. So we have subduction going on to the northwest up here. This is causing volcanism up in the Sumatran Arc, the Banda Arc. Up here, we have active collision going on in Papua New Guinea. The Australia plate is colliding with Papua New Guinea up here. We also have active collision going on over in New Zealand. The North Island of New Zealand is actually on the Australia plate. The South Island is on the Pacific plate. New Zealand straddles those two boundaries, and we have spreading ridges down to the south here. So these here, these black arrows, these are indicating places where we have mid-ocean ridges. So this is a place where tectonic plates are splitting apart in the middle of the ocean. We're creating new oceanic crust down here. It's these spreading ridges, these are moving quite fast, and these are effectively pushing Australia, the whole plate, up to the north. And that's one of the main things that's driving this active collision that's going on up to the north of our country in the modern day. So this is the modern day picture of Australia. And as I said, we're one of the most active intraplate seismic zones in the world. So there are 4 main seismic zones in Australia. These are labelled on this map here. We have the northwest seismic zone up in northern Western Australia. We have the southwest seismic zone in southwestern Australia. We have the Flinders seismic zone, which is in South Australia around the Adelaide area, and we have the southeastern seismic zone, which is in New South Wales, Victoria, and parts of Tasmania. And this seismicity is really driven by the fact that we are moving so rapidly. We're moving at 7 centimetres per year, and these far-field stresses at these plate boundaries are actually affecting the continent itself. So that's what's driving a lot of this seismicity. It's the product of this horizontal compression and uplift. Before I go too far, I want to introduce some terms to you. Some of these terms will be extremely familiar to you, and some will be terms that you may not have come across before in Geo 110. So some terms like supercontinent, you would have heard of supercontinents before. We talk about Pangaea in 110, but some of these other terms might not be familiar to you, and I'm going to be using them over the course of this lecture. So I just thought I'd put some definitions up here. Some of the important ones include the word craton. You might not have come across craton before. These are really stable parts of Earth's crust that have been around for at least 1 billion years, but in most cases these cratons have been around since the Archean, so over 2.5 billion years. So these are really proto-continents. These are the earliest sort of continental crust. They're really stable, they're really buoyant, they're very difficult to destroy, so they sit up on the Earth's surface for very long periods of time. The term supercraton is also in here. This is similar to a supercontinent, but these are older. Supercontinents are what we see in the modern day. Supercratons are what we saw back in the Archean, where the only material around was these smaller cratons, and they collided together and they joined together just like the supercontinents do in the more modern environment. If I use the word element here, I'm not talking about chemical elements in this case. I'm talking about parts of continental crust, so a broad area that shares a similar sort of geological history. And there's a number, I won't read through all of these terms, there's a number of other terms here. If I say something and you don't understand that particular terminology, this might be a good place to look. You should all be familiar with the geological timescale. We talk about this a fair amount in Geo 110. As I said, I'm going to be working through the history of Australia, starting from the beginning, working through to more or less the modern day. Today's lecture, I'm going to be focusing on pre-Cambrian Australia, which is this section of the geological timescale here. The pre-Cambrian goes from the formation of the planet, which occurred about 4,600 million years ago, through to the end of the Proterozoic, which ended around about 540 million years ago. So this is about 4 billion years of history here. By contrast, this area, which is really expanded out, I'm going to talk about this in the next lecture, this is only 500 million years, so about 0.5 billion years of Earth's history here. So although this is expanded out, this is actually a significantly shorter period of time than the pre-Cambrian. So we're going to be rushing through 4 billion years of history in today's lecture. So before I go on too much, I've got to talk a little bit about how do we determine the ages of things. And again, this should be revision to you from Geo 110. In Geo 110, we talk about relative ages and absolute ages. Relative ages, we use the relationships of rock masses to one another to determine which one is older and which one is younger. Relative ages don't give us a number. They won't tell us that this rock is exactly 1 billion years old, but it will tell us that this rock is older than this other rock because the other rock cross-cuts that first one. So you're looking at those sorts of relationships. Fossils are also useful for determining these relative sorts of ages. So there's a fossil scale that's been put together to determine the relative ages of rocks. However, if we want to know the absolute age of the rock, so if we want to know if a rock is 100 million years old or a billion years old, we need to rely on absolute dating techniques, and the most common of these is radiometric dating. The radiometric dating relies on the radioactive decay of particular isotopes and looking at the ratio of those isotopes to their parent isotope within the rocks. There's a number of different systems that are used, including the ones listed here. These are the most popular ones in geology: potassium, argon, 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 rubidium, strontium, uranium, lead, thorium, lead, samarium, neodymium, and rhenium, osmium. There's new isotopic systems being used and developed all the time, but these are still the most common ones that we use in geology. The most commonly deployed of these techniques is uranium lead, and this is normally done in the mineral zircon. The reason we use zircon is because zircon contains a significant amount of uranium in it, and this uranium decays to lead. One of the things you need to know when you're determining the age of these rocks, and you might remember this from one of the early pracs in Geo 110, is you need to know how much of the initial parent and daughter isotope that you have within that particular mineral. And zircon contains no lead, but it has a significant amount of uranium. So the initial lead to uranium ratio is going to be 0. We know that. So that gives us a good starting point for calculating out the age of rocks. So that's why zircon is commonly used. Now, speaking of zircons, the oldest mineral grain on the planet, or the oldest mineral grains that we know of on the planet, are found in Australia, in Western Australia, and these are zircon grains. These are detrital zircon grains that are found in sandstones in the Jack Hills province, north of Perth. Here's a map. Perth's here. Jack Hills is north of Perth, up here, significantly north of Perth, in these sandstones here. These zircons have been dated using uranium lead techniques, like I mentioned on the previous slide, using a method called shrimp, and they have been determined to be 4.4 billion years old. So they're about 150 million years younger than the Earth itself. We know the Earth is older than these grains through meteoritic studies. So we basically date meteorites and assume that the Earth formed at the same time using various accretionary models. So these are the oldest grains that we know of on Earth. Now they didn't form in the sandstone. Zircons form within granitic melts. That granite would have formed. It would have been eroded. That eroded material was transported as sand, deposited, and formed into this sandstone. So the sandstone itself isn't 4.4 billion years old. The sandstone is only something like 2.6 or 2.7 billion years old. It's significantly younger than the grains within it. But the grains have been dated as 4.4 billion years old. So the other thing about zircons is you can do various chemical techniques on them, and you can determine things like the temperature of formation and start to figure out a little bit about what the temperature of the Earth was like when these crystals were crystallizing. And some of the studies that have been done on these Jack Hill zircons have indicated that the Earth was probably cool enough when these were forming to have liquid water on the surface of the Earth. So this means that the Earth must have cooled down significantly in that first 150 million years. I think when we all picture the early Earth, we picture this vast ocean of magma. It's a really chaotic sort of place. But there must have been some parts of the planet that were already cool enough to have liquid water on the surface within 150 million years of it forming. A very recent study, in fact, these zircons have been subject to many, many studies. They really are only evidence of what was going on back in this point in Earth's history, back in the Hadean. A recent study has indicated that these zircons probably actually crystallized in something called an andesitic magma. The thing about andesitic magmas is they form specifically in subduction environments. Now that's interesting because it means we had subduction going on already 4.4 billion years ago. There's a lot of debate in the earth sciences about exactly when plate tectonics started. Some people will stretch it all the way back into the Hadean, like this study was suggesting. Other people don't think it started until towards the end of the Proterozoic, only 600-700 million years ago. So there's this debate that's been going on now for over a decade about when exactly did tectonics start? Has tectonics always been operating on the planet, or did it start significantly after the planet's formation? And this is one piece of that puzzle that people have been looking at these zircons, and the recent study indicated that we may have had some form of tectonic, some form of subduction going on all the way back in the Hadean, which is interesting in itself. This is a geological map of Australia, and the different colours on this geological map indicate the different ages of the rocks. Now, one thing you might notice when looking at this map is a lot of Australia looks like it's covered in this yellow material. So pretty much most of the centre around here has this quite yellow sort of colour. And if we go up and look at the key, that relates to the Cenozoic and the Quaternary. These are very recent parts in Earth's history. So the Cenozoic started at 65 million years ago. The Quaternary is only a couple of million years ago, so something like 2 MA. So these are very recent sort of materials. But the thing is, most of this material is really just cover. It's really just soils, colluvium, alluvium, material that's been transported on the surface. This isn't really the age of the rocks underneath the ground. This is the age of the rocks right on the surface. So this is effectively regolith material here. So when we look at the map like that, it looks like Australia is actually pretty young, even though we talk about it being a very ancient sort of continent. If instead of looking at a map like that, we try and strip that material off the surface, so there's various studies that have been done trying to look at what's deeper underneath that regolith and look at the age of those rocks, this is the sort of map that we come up with. So again, this map is split up based on the ages of these different terranes and these different areas within Australia. But in this case, we've taken off all of that really recent sort of cover. So the brownish colours here, these represent Archean rocks. Archean to Proterozoic. These are really old sorts of rocks. The Archean ended at 2,500 million years ago. So you can see there's a lot of these in Western Australia. Central Australia is dominated more by these Proterozoic rocks, these sort of pinkish sort of colours. So around here and down here, these are the Proterozoic rocks. The Proterozoic ended at the end of the Precambrian, about 540 million years ago. And Eastern Australia is really quite strongly dominated by the Phanerozoic rocks. So we've got a lot of greens and blues over here. So these represent the Paleozoic, which is the oldest era within the Phanerozoic, and the Mesozoic. And then there's a spattering of Cenozoic material around too. Most of the Cenozoic is simply cover on the surface. And here's taking that same map and then simplifying it basically even further. So in this case, red indicates Archean. This is old stuff. The olive colour, this kind of browny olive sort of colour here, that represents Proterozoic. So this ranges from 2.5 billion years ago to about 500 million years ago. And the purples, greens and yellows represent the Phanerozoic. One thing you might notice on this map is that the really old material is very strongly concentrated in Western Australia. Western Australia is made up of a lot of really, mostly Archean rocks with a bit of Proterozoic in there. Central Australia is made up a lot of these Proterozoic rocks. We have a lot of these olive-coloured materials in here with a little bit of Paleozoic spread through there as well. And Eastern Australia is made up mostly of these green, yellow and purple rocks. These are the Phanerozoic rocks. So these are really old. This is old material. This is kind of somewhere in the middle. And this is the young Australia over here. In fact, I won't talk much about Eastern Australia today because I'm only going to be talking about the Precambrian. Most of Eastern Australia didn't exist in the Precambrian. So people say Australia has grown from west to east. The oldest material is in Western Australia. Central Australia is made up of things in the Proterozoic, somewhere in the middle, and Eastern Australia is made up of pretty young material. So what I want to do now is kind of go through some time slices and some explanatory notes about the evolution of our country. So I'm going to show some cartoons and some explanations of those cartoons. So firstly, let's just strip off all that material off that previous map that I showed, other than the stuff that is Archean in age. So the Archean is the era that ended 2,500 million years ago. And hopefully you remember from Geo 110, this term MA stands for millions of years. So I'm talking about millions of years ago here when I say MA, 2,500 MA. Now, most of the Archean stuff, as we saw on that previous slide, is sitting in Western Australia. There's two large cratons in Western Australia, both of which are Archean in their age. The Yilgarn Craton, which forms pretty much the lower half of the state, and the Pilbara Craton up in the northern part of the state. There's also a spattering of Archean material around other parts of Australia, most notably in South Australia, where we have parts of the Gawler Craton, and also up in the Northern Territory, where we have some material up around Pine Creek. The Pilbara Craton is really the oldest part. This is the oldest part of the Australian crust. This cratonized around about 2800 million years ago. So when I say cratonized, I mean it formed a craton. And remember I mentioned right at the beginning that term craton means a stable bit of crust. So it's basically been stabilized. It hasn't really been modified much since that point in time. So there might have been a little bit of deformation around the margins, but when we say it's cratonized, basically it's become a stable element of continental crust. It hasn't really changed much since that point in time. Maybe a bit of erosion, maybe a bit of deformation around the edges, but ultimately it's been a coherent body for that period of time. So definitely within the Archean. So there's older parts, there's older rocks within the Pilbara. There was older material that came together and has been cratonized 2,800 million years ago. The Yilgarn Craton was cratonized somewhere between about 2,700 and 2,600 million years ago, and the Gawler Craton was cratonized around about 2,500 million years ago. There's a large epicratonic basin in the Pilbara Craton that resulted from the sagging and early sedimentation within this craton. So that's this little white bit through here. This is the Hamersley Basin. This is where the majority of Australia's iron ore sits. The Hamersley Basin is enormously important to Australia's economy. That's where a lot of the iron ore is sitting. There's also a number of other mineral deposits that occur within Western Australia, within these Archean rocks, most notably Australia's gold. About 70% of Australia's gold is from the Archean, and a lot of that comes from the Yilgarn Craton, somewhere around about here, around about where Kalgoorlie is, and the surrounds. That's the Western Australian goldfields. I know there's large gold deposits in other parts of Australia, things like Bendigo and Ballarat, but the majority of Australia's gold is actually in Archean rocks in Western Australia. And same with some other important deposits as well. Things like nickel. A lot of Australia's nickel is also sitting in the Yilgarn Craton. So a lot of Australia's mineral wealth had already formed back in the Archean. These are really old deposits that are being mined. In the Archean, we had the earliest continental crust developing in Australia. These were developed first in the Pilbara Craton and then in the Yilgarn Craton. The Pilbara Craton contains some of the oldest rocks in the world. We don't quite have the oldest rock in the world, but we have some of them. There are rocks dating back pre-3.5 billion years ago in the Pilbara Craton, and similar sorts of time in the Yilgarn, although the majority of the Yilgarn actually formed later on. The Pilbara Craton also contains some sedimentary rocks that contain some of the earliest signs of life. It's always debatable about when exactly life started on Earth, but some of the oldest uncontroversial fossils come from the Pilbara Craton. Now, these are only single-celled fossils, they're bacteria, and one of the leading places for the oldest fossil on Earth is in the Strelypool Chert, which is a rock unit that you find within the Pilbara. These rocks are about 3,500 million years old, and they have these fossilized bacteria within them. There's some evidence that life evolved earlier on Earth. There's some chemical and isotopic evidence that it was around 3.8 billion years ago, but the oldest real fossils that we know of come from the Pilbara Craton. So this is quite an important sort of discovery. As I mentioned earlier in the lecture, there's a lot of debate about exactly when plate tectonic processes started as well. The recent study in the Jackal zircons suggests that it might have been, we might have had active subduction going on all the way back to 4.4 billion years ago. But that's still, a very debatable sort of point, and there's a lot of people who have a very different opinion to that. So a lot of people would say that there were not normal plate tectonic processes occurring in the Archean. Instead, we had these thick oceanic plateaus and these large mantle plumes, and we had more of a vertical sort of tectonic scenario going on. So if we think about tectonics today, we have these horizontal plates, or these plates that are moving around horizontally on the Earth's surface, and we have the oceanic plates subducting underneath these continental plates as a result of these density contrasts. Back in the Archean, we didn't really have much, if any continental crust. So we couldn't really have subduction going on. We couldn't have this normal sort of regime. But what we did have is these large blobs, these large plumes coming up from underneath. these cratons and starting to cause deformation in a more vertical sort of sense. And so this has been termed vertical tectonics, and that's probably what was operating in the Archean around the time when the Pilbara Craton was forming. And I'll show a picture of some of these large blobs that were probably parts of these mantle plumes in a later lecture slide. Most of the crustal development occurred in the Yilgarn Craton between 3,000 and 2,700 million years ago in what are called greenstone belts. Greenstone belts are belts of mafic, ultramafic and felsic volcanic rocks, as well as some sedimentary rocks associated with them. So these are ancient volcanic belts and sedimentary basins. These form these linear sorts of belts that are common in these Archean cratons. As well as having these greenstone belts, we also later had formation of significant granites that were emplaced within the Yilgarn Craton. In this case, somewhere between about 2,700 and 2,600 million years ago. These granites have low density. If you remember back to GL 110, we talked about the density of felsic versus mafic magmas. Felsic magmas have a lower density, and when they're emplaced within this crust, it caused this crust to have a really strong buoyancy. It meant that that crust was very difficult to ever subduct back down into the mantle. And this is the reason why continental crust is so much more stable than oceanic crust. If you remember, oceanic crust is primarily made out of basaltic material, so it's quite dense, whereas continental crust is more felsic sort of material, so it's quite buoyant. And it was the emplacement of these granites within these cratons that really ultimately led to their stabilization. So after we had the formation of these greenstone belts, we had the intrusion of these more granitic magmas, stabilizing that crust and turning it into a craton. So taking it from bits of crust that could easily subduct back down into the mantle to something that was a bit more buoyant and going to be stable and has now been sitting around on the Earth's surface for over 2.5 billion years. Now, this is something that we see in the Yilgarn and the Pilbara Craton, but if you look at cratons around the world, similar sorts of processes seem to have been operating where we have this stabilization of the crust through the emplacement of these granites. So we had over 600,000 cubic kilometres of granite intruding into the crust between 3,000 and 2,600 million years ago. That's an enormous amount of material. Here's a picture of the Pilbara Craton up here. This is the Pilbara Craton. We have a couple of different images of the Pilbara Craton here. This is the Landsat image. We also have various geophysical images here. This is the gamma ray image. The gamma ray image is looking at the gamma rays that are emitted through the radioactive decay of materials, especially anything that contains uranium, thorium, or potassium. So that's what we're seeing here. This is the magnetics image, so how magnetic these rocks are, and D is the gravity image, so we're looking at the density here. And one thing you can see quite clearly on both the Landsat image as well as the gamma ray image are these sorts of blobs that we see here, these lighter coloured blobs. These are granites. So these are the granites. These are large bodies of granite that have intruded into this craton and effectively stabilised it. So this is these are these large plumes that intruded up. We had this kind of vertical tectonics going on, these large plumes intruding into this craton and stabilising it back in the Archean. This is the Yilgarn Craton. So before I was looking at the Pilbara Craton, this is the Yilgarn Craton. This comprises thin attenuated greenstone belts and surrounding granites. Again, those granites stabilise this crust. We also have large areas of gneiss. Remember, gneiss is a metamorphic rock. In this case, they're mainly granitic gneisses in the west. And the ages in the Yilgarn Craton, like a lot of the rest of Australia, get younger from the west to the east. So the oldest parts of the Yilgarn Craton are here. And these lines here are basically indicating different terranes. So the Yilgarn Craton isn't just one giant rock. It's obviously made out of multiple different rocks. And it's made out of multiple different terranes. So these are major boundaries within the Yilgarn Craton. Although we talk about it like it's a single mass, it's actually been built up over a long period of time in itself. And it's primarily been built from the west, these really old sorts of things, towards the east. So this is the younger terranes out here. These yellow dots that are shown here, these are indicating gold deposits. As I said, a lot of Australia's gold, 70% of Australia's gold is sitting within Archean Australia, and most of that is actually sitting in the Yilgarn Craton. In fact, there's very little gold in the Pilbara Craton. There's a little bit in the Gawler Craton in South Australia, but by far the majority of Australia's gold is actually sitting in the Yilgarn Craton. And it all happened more or less within a geological weekend, somewhere around about 2.7 billion years ago. That's where we had most of Australia's gold forming, around about that point in time, and mostly forming in this particular terrain here. This is the Kalgoorlie terrain. This contains most of Australia's gold, this thin slither of the belt up here, including Australia's largest deposit in Kalgoorlie, and by some estimates, that's actually the largest gold deposit in the world. So it's an enormous amount of gold that's been pulled out of here. Again, this is a map of Western Australia, showing once again that the Yilgarn Craton is made out of these greenstone belts, which here are shown in a green colour, and they're surrounded by granites and gneisses in these more pinkish sort of colours. As I mentioned, Kalgoorlie is the largest gold deposit in Australia, and by some estimates the largest in the world. Some of you might have been out to Kalgoorlie, especially if you're from Western Australia. I grew up in WA and I got to go out to Kalgoorlie a few times. It's a really quite an interesting town. This is the town here. The town varies in size. I think at the moment it's got somewhere around about 30,000 people living there, but it fluctuates depending on what the mining industry is doing, somewhere between about 25,000 up to about 50,000 people. So it's a sizable town. It's comparable in size to Armidale, where I live now, and many of you have visited for intensive schools. And this is the mine. And you can see here already the mine is similar sort of size to the town itself. So this is an enormous mine. An enormous amount of gold has been pulled out of this thing, and it's still active today. So they're still digging this super pit up today. So this is one of the largest gold deposits in the world, and it's sitting in these Archean greenstones in the Yilgarn Craton. Okay, I've been talking a lot about the Archean. So the Archean ended at 2,500 million years ago. Now we'll move on to the Proterozoic. And the Proterozoic is split up into three major divisions. The Paleoproterozoic, which I'll talk about first, that's the oldest part of the Proterozoic, then the Mesoproterozoic, and then the Neoproterozoic is the youngest part of the Proterozoic. So we'll start off in the Paleoproterozoic. This goes from 2,500 million years to 1,600 million years ago. The Paleoproterozoic was a major period of continental crust, particularly around these Archean nuclei, and then to the east extending into Western Queensland and Western New South Wales. So in the Archean, we formed these nice stable sorts of cratons. Now in the Proterozoic, we started building on that material that was already there. We started building around those things, and we also started joining those cratons together. Just go back a bit, we keep talking about maps like this, but remember, these things actually formed quite separately. The Pilbara was probably joined to South Africa at the time. Western Australia was probably joined to Canada at the time, or to the part of Canada at the time. So these two weren't actually joined. Australia didn't look like this. Obviously, the coastline didn't exist at the time. These things weren't joined. They've been subsequently joined together in later events, and these events occurred in the Proterozoic. So we'll talk about those in a minute. So we formed those nuclei, those cratons, and we're building around them and starting now to shuffle these cratons around on the surface of the Earth, like we do with modern tectonics, and starting to join things together. In the Proterozoic, there's evidence for the first major continents, the first glaciations, and the first evidence of complex life. So I'm talking about multicellular life here. In the Archean, as I said, there's evidence for bacterial life, but once you get into the Proterozoic, you start seeing evidence of this multicellular life. By 1,600 million years ago, the three Archean crustal elements of Australia were assembled. So we basically formed kind of a proto-Australia by sticking together the Yilgarn and the Pilbara Craton. These were joined together around about somewhere between 2,200 to 1,900 million years ago. And this was a really prolonged period to do this, to join these two together. It took 4 orogenies to stick these two together. Orogenies, remember, these mountain building cycles. So we went through 4 of these mountain building cycles to stick these two cratons together and form Proto-Western Australia, or what we often call the Western Australian element. We don't know how far these were apart initially. The further we go back in time, the less we know about things you'll discover. So we don't initially know how far apart these two were formed. This forms, when these two did join together, this forms the Western Australian element, and this was part of a supercontinent called Nuna. You've come across supercontinents before in Geo 110. We often talk about Pangaea. Pangaea is probably the best studied and the best understood supercontinent, but it's one of many supercontinents that have been on the surface of the Earth over time. So Nuna was a supercontinent that existed in the Paleoproterozoic. And again, we still don't know a lot about Nuna. There's still a lot of active research that's being done to try and understand which elements were sitting where within this supercontinent. We had growth of continental crust over large areas of northern, central and southern Australia during the Proterozoic through the deposition of sedimentary and volcanic rocks in rift-related epicratonic basins. This occurred between about 2,000 and 1,700 million years ago. We also had subsequent deformation and metamorphic events and emplacement of granitic magmas during the Paleoproterozoic. Significant amounts of basaltic volcanism and magmatism up in the Mount Isa region in Queensland. We had the Tanami-Tennant Mount Isa province and the Kimberley-Pine Creek province amalgamating around 1,800 million years ago, and this formed the North Australian element. So it formed the Western Australian element by about 2,000 million years ago, and after that we formed the North Australian element by joining these pieces together. And Proto-Australia was probably linked to North America at around this time. So these are the different jigsaw piece puzzles, I guess, of Australia, the bits and pieces that we had available at this point in time to start joining together. So these things were starting to be joined together during that Paleoproterozoic. So in the early Paleoproterozoic, we had these various different elements that were just floating around on the Earth's surface but weren't actually joined together. So we had the Pilbara Craton, we had the Yilgarn Craton, we had the Glenberg terrane. These eventually joined up by about 2,000 million years ago. And when they were all joined together, they formed the Western Australian element. We also had various parts of Northern Australia, things like Kimberley, Pine Creek, the Proto-North Australian element, Aileron, and a few other terranes, and these were all joined together by about 1,800 million years ago, and we called this the North Australian element. The South Australian element was also amalgamating at this point in time. There's a lot less that's actually known about the South Australian element, so we've still got a lot of active work to do there. As I mentioned, it was a prolonged period actually joining the Pilbara Craton to the Yilgarn Craton. So this is a little cartoon showing what was going on. We had the Pilbara and had subduction going on underneath Gascoyne. This eventually joined the Pilbara and the Gascoyne together. Subsequent to that, we had subduction going on from the Yilgarn Craton under the Gascoyne, and that was joining the Yilgarn Craton to the Gascoyne. And effectively, this is how we started to amalgamate this Western Australian element, joining these pieces together. The Kimberley Craton was joined to rocks extending down to Tennant Creek and across Arnhem Land in Mount Isa by the end of the Paleoproterozoic. We'd had more crust added onto the Gawler Craton. Remember, this is the craton in South Australia. This had been enlarged and extended out to Broken Hill by the end of the Paleoproterozoic. We had significant amounts of basaltic volcanism going on during the Paleoproterozoic, including considerable amounts of basaltic volcanism going on around Mount Isa, the Arunta region, and the Arunta region near Tennant Creek between 1,800 and 1,700 million years ago, as well as basaltic volcanism going on in the Gawler Craton between 1,600 and 1,500 million years ago. Australia is quite famous for having this style of metamorphism at this point in time. We had a lot of high temperature, low pressure metamorphism going on. So if you think about contact metamorphism is often high temperature, low pressure, because what's driving that metamorphism is the high temperature of an intrusive body. In Australia, during the Paleoproterozoic, we had a significant amount of high temperature, low pressure metamorphism going on that probably wasn't necessarily associated with intrusions. This might have been through crustal thinning and the upwelling of the mantle to fill up that area that resulted from that thinning of the crust. So we had extensive, regional scale, high temperature, low pressure metamorphism that was going on at this point in time. It's something that's pretty much unique to Australia. There's probably examples of it elsewhere in the world, but certainly at this large sort of scale, We see it mostly in Australia, mostly within the Proterozoic, especially the Paleoproterozoic. So there's a number of different areas that saw this high temperature and low pressure sort of metamorphism. By the end of the Paleoproterozoic, we had formed these elements. So we had the Western Australian element. This has now been all joined together. We glued the Yilgarn Craton to the Pilbara Craton. We had also formed the North Australian element, so we'd stuck all of those components together, and the Gawler Craton had continued to grow outwards, especially outwards towards to the east, out towards the Broken Hill sort of area. So these things weren't actually joined together yet. We hadn't actually joined South Australia to North Australia to Western Australia, but the individual elements were there, ready to be joined together later on in the Mesoproterozoic. During the Mesoproterozoic is the middle part of the Proterozoic. It runs from 1600 to 1,000 million years ago. And during this time, we had continued deformation, metamorphism, and emplacement of intrusions, especially granites and gabbros, in the mobile belts in Western, Central, and Southern and Northern Australia. There's a number of these events that go on through Australia at this point in time. This process led to further eastward growth of the continental margin, and we had also the development of major epicratonic rift-related basins. So epicratonic means within the cratons, or within these elements. So these elements were also starting to thin out, and were starting to form these basins as a result of rifting within them. There's a number of major resources within the Mesoproterozoic, especially some large base metal deposits that were going on at this point in time. Places like Broken Hill and Mount Isa, a lot of the base metal deposits were formed during the Mesoproterozoic. And we also had some diamond deposits forming. Some of a significant amount of the world's diamonds comes from the Argyle diamond mine up in northwestern Australia. We also had BIFs forming at this time in the Hamersley Range, so this has provided a lot of Australia's iron ore. So here's some of the locations of these large deposits, and these are all world-class deposits. Some of the largest deposits on the planet are within Australia, forming within the Mesoproterozoic. Generally not a huge amount of gold at this point in time. There's really a lack of gold within the Mesoproterozoic, but we do see a number of other really significant sorts of deposits. The ones up around the Mount Isa region, Broken Hill is one of the world's largest lead-zinc bodies. Olympic Dam, this is an iron oxide copper-gold deposit, again, one of the world's largest deposits sitting within South Australia, and the Argyle diamonds sitting up in northwestern Australia. Here's a picture of some of these mines. These are pretty famous parts of Australia and really quite famous geologically around the world. Broken Hill is where BHP got their start. If you didn't know, BHP stands for Broken Hill Proprietary, the world's largest mining company, and it started in Broken Hill in Western New South Wales. We run a number of student field trips out to Broken Hill. If you stay on to third year, you might be lucky enough to come with us out to Broken Hill. The rocks out there are spectacular. Again, this is an area that's famous for this high temperature, low pressure sort of metamorphism. The rocks out there have been really cooked up, and it has one of the world's largest ore bodies out there. Really spectacular rocks, really interesting part of the world. Also Mount Isa and Olympic Dam, two of the largest ore bodies in the world. Mount Isa is more, I guess, a series of ore bodies rather than a single mine, but yeah, really interesting parts of the world, these. Something else that happened during the Mesoproterozoic was the formation of the next supercontinent. I talked about Nuna earlier on, but one of the next supercontinents in the supercontinent cycle was Rodinia. Rodinia started to amalgamate during the Mesoproterozoic. It took really quite a long time for it to amalgamate, between about 1,300 and 900 million years ago. At this point in time, Australia, or what existed as Australia at the time, was largely an intraplate landmass, and we're probably sitting next to Laurentia. Laurentia is mostly North America now. When you think about Laurentia basically as being North America. So Australia was sitting right next to North America at this time. The Western Australian element was stable at this point in time, but it was starting to get reworked along its boundaries. So we had the Patterson origin, this was going on in the northeast. We had the Albany-Fraser origin, this was going on along the southeast. And we had the Pinjarra origin, which was going along on the west coast of Western Australia. So Western Australia was basically getting pushed from all sides at this point in time. We had these various orogenic belts forming. So we would have had mountain belts basically surrounding the border of Western Australia at this point in time. Mineral deposits formed at this time were a little bit different to the ones in the older orogenies and the younger Gondwanan systems. As I mentioned before, there was a real distinct lack of gold at this point in time. Most of the older orogenic systems had what we call orogenic gold. There's a lot of gold associated with those mountain building processes. Real lack of it in Rodinia. It's always been a little bit of a mystery as to exactly why that was, what was wrong, or what wasn't present to form these large systems. There's an abundance of diamonds at this point in time. There's nickel, copper, PGE deposits, and there's some rare earth element deposits. So there's not a complete lack of economic deposits, but there is a lack of certain types of economic deposits during Rodinia. The breakup of Rodinia resulted in the formation of something called Tasman Line. I'll explain what that is on a map in a minute, but it's basically a boundary that separates Eastern Australia from the western two-thirds of the continent. So it separates pre-Cambrian Australia. Remember, right in the beginning of this lecture, we talked about how Australia has grown from the west to the east. Pre-Cambrian Australia is the Proterozoic and Archean Australia, the western two-thirds of the continent. Phanerozoic Australia is really the eastern third of the continent, and the line separating those is called the Tasman Line. So this is more or less what Australia actually looked like at this point in time. This is obviously a bit of a schematic sort of cartoon, but this is pretty much what Australia would have looked like. We had the Western Australian element, the Northern Australian element up here, and the South Australian element down here. And these were starting to get glued together by these orogenies. So we had the Patterson orogeny that was effectively joining Western Australia to Northern Australia. We had the Albany-Fraser origin along here, which was joining Western Australia to Southern Australia. And we also probably had the Patterson orogeny, the Pinjarra orogeny going down the western side of Western Australia. So this is what Australia looked like at the time. And this line here, I haven't shown any Eastern Australia on this map because Eastern Australia still effectively didn't exist at this point in time. This is the Tasman Line. Tasman Line. So this separates out the western two-thirds of the continent, old Australia, ancient Australia, from the Phanerozoic Australia, the young stuff, which still wasn't existing at this point in time. We had a lot of deformation going on in this point in time. We see a lot of folding, a lot of faulting. So I've got a couple of photos here from Central Australia. This is a photo from near Alice Springs. You might be able to make out from this aerial photo some of the deformation that's going on. So we can see some folding that's going on around here. There's also a number of faults that are cross-cutting through these rocks here. So we've actually offset this rock unit like this over here. And there's another fold that's more or less running around down here. This probably bends back around on itself like that. And so this area is actually really quite deformed, and a lot of this deformation was going on at this point in Australia's history around Central Australia. So that's around Alice Springs. We see similar sorts of deformation a bit later on in the Flinders Ranges. So these are younger sorts of rocks, but these also went through a significant amount of deformation in the Proterozoic. You might see here, this is what we call a synform. It's a folded rock. This is quite a broad, open sort of synform. But these rocks here have been quite folded. This folding was occurring during the Proterozoic. Here's an aerial photo of the Flinders Ranges. And again, hopefully you can see these rocks are basically bent around like this. So there's some quite tight folding that's actually going on within these rocks. There's a significant amount of deformation that's associated with some of the orogenesis that was going on during the Proterozoic. So here's another map of Australia, simplifying it down into those various elements that I've talked about a few times now: the North Australian element, the Western Australian element, and the South Australian element, and the orogenies that had joined these together. So we had the Patterson orogeny that was joining together Western and Northern Australia, Albany-Fraser origin joining together Western Australia and South Australia, the Musgrave origin joined together South Australia and North Australia, and then the Pinjarra origin down the west coast of Australia. And then we had the Tasman Line here And so none of this part of Australia at this point in time existed. Between 1300 and 700 million years ago, we had the formation of the supercontinent Rodinia. This had broken up or started to break up by 700 million years ago. The western two-thirds of Australia during the Neoproterozoic was cratonized. So effectively, this stuff here had now formed. I might just change color to make that a little more obvious. So basically, this stuff here had now formed, joined together, and this is now cratonized. So again, cratonized means that it's now a stable bit of crust. We can rework the edges, we can deform around the edges, but not a lot happens within the center of these cratons. So there might be bits of deformation. We know there's some seismic activity and various, you can get volcanism and things through the center, but effectively this is now a single element. This has been joined together and it's going to stay that way more or less forever. So the western two-thirds of the continent had been cratonized by the end of the Neoproterozoic. Oh yes, I should say the Neoproterozoic runs from 1,000 to about 540 million years ago. So we're now talking about the end of the Proterozoic, the last part of what I'm going to be talking about today. And we had formed that Tasman line. So everything else occurred basically in the Phanerozoic, and I'll talk about that in the next lecture. We had some widespread epicratonic sedimentation across northern, central and southern Australia and the filling of rift basins covering this older crust at this point in time. So we had things like the Adelaidean rocks being deposited. These are effectively what make up the Flinders Ranges all the way through to about Broken Hill. There's the sedimentary cover sitting on top of those more ancient Proterozoic rocks. We have evidence of two periods of really widespread glaciation occurring during the Neoproterozoic. These are part of that snowball Earth story. I talked about this in Geo 110, where effectively the whole planet had frozen over into a giant ball of ice. The oceans are completely frozen, and we had glaciers from the poles all the way up to the equator. At this point in time, Australia was sitting pretty close to the equator, within a few degrees, I think within about 10 degrees of the equator, but we had glaciers covering central Australia at this point in time. Towards the end of Neoproterozoic, we have the first uncontroversial multicellular organisms forming. There is some evidence of multicellular organisms earlier in the Proterozoic, but by the Ediacaran, which is the end of the Neoproterozoic, we really have uncontroversial multicellular life. These are soft-bodied organisms rather than the things that have bones and teeth like what we have today. These soft-bodied organisms formed towards the end of the Ediacaran. We had deformation and metamorphism in central and northwestern Australia, little continental growth eastwards during the Neoproterozoic, except for a little bit around South Australia. And again, we have a number of ore deposits that had formed at this point in time. As I said, there was extensive glaciation during the Neoproterozoic. There's evidence of the earliest glaciation event. The evidence for the earliest glaciation event includes rocks that stretch from the Kimberley region all the way down through Alice Springs, down through Alaria in South Australia to Broken Hill and to the Flinders Ranges. These rocks are called tillites. They're very poorly sorted sediments that result from the transportation of sedimentary material and erosion by ice. So these are glaciers moving over the surface, transporting this material and depositing it into really poorly sorted sediments. We see this wherever we see glaciation today. The major glaciation events occurred between 780 million years ago to 700 million years ago, and a second event that occurred between 610 to 575 million years ago. This second glaciation, this event, occurred just before the Cambrian explosion of life, and there are some people who try and link together these two events. Basically, they figured that the ending of that glaciation period might have pumped evolution, resulted in new niches opening up, and the result of the Cambrian explosion of life. So here's the map of Australia, and these dots, these bits through here, these are areas where we see these glacial deposits, these tillites. So these occur all the way through the centre of Australia, from the Kimberley up the top here, through Alice Springs, down to Broken Hill, through the Flinders Ranges. So we have a lot of glacial rocks sitting through the centre of Australia, indicating that we had widespread glaciation at this point in time in the Neoproterozoic, while Australia was sitting more or less on or near the equator. So as I said, the paleomag studies indicate that we're close to the equator at this point in time, and we're seeing these glacial rocks. Here's a picture of one from Malari, these poorly sorted sediments. These are these tillites that formed around about 600 million years ago as a result of that glaciation. Australia's position during the Neoproterozoic was sitting next to Laurentia and Antarctica. So this is what Australia's outline more or less looks like. We joined together those elements, as I've said several times, and we were joined ourselves to Laurentia as well as to Antarctica as part of this supercontinent Rodinia at this point in time. Glaciation would have affected the oceans, of course. One thing that was occurring at this point in time is the oceans are freezing over, so the oceans would have been icy, and that resulted in the separation between the oceans and the atmosphere through this layer of ice that sat between the two. Of course, ice floats, so it's going to be sitting on top of the oceans, and that's going to separate that liquid ocean, the deeper ocean, from the oxygen-rich atmosphere. And as a result, once again, the oceans became oxygen poor. As organic matter started to decay, it used up the oxygen that was sitting within the oceans. The oceans were now closed from the atmosphere, so no new oxygen was being introduced into the oceans. And as a result, the ocean chemistry changed dramatically. The oceans became anoxic, and as a result of them being anoxic, they could start dissolving iron. I talked about this in one of my 110 lectures, where I talked about the formation of these banded iron formations. Iron is soluble in anoxic conditions, it's insoluble in oxic conditions. So as the oceans became anoxic, they could start once again dissolving iron. So all these rocks that are in contact with the oceans, they would start leaching their iron out into the ocean. The oceans would become iron rich. When we had the end of that glaciation period, we melted that ice layer that was separating the oceans from the atmosphere. Oxygen could once again be introduced into the ocean. We started getting oxic conditions again, and as a result, that iron started precipitating out and would form banded iron formations. So we saw the majority of the banded iron formations forming at the end of the Archean when we had that great oxidation event, but we also see banded iron formations forming during the Neoproterozoic after these glaciation events. All right, I've gone through a lot. I've gone through it quite quickly, but I've talked about the history of Australia, the first 4 billion years, from the earliest crystals that we saw through to the glaciations that ended the Proterozoic. I'm going to give a second lecture on the geology of Australia, where I'll talk about the last 500 million years of Australia's history. Mostly this is the Phanerozoic, and I'm going to be talking about the formation of a lot of Eastern Australia in that point. So I hope you found this interesting. Australia is a really interesting place to do geology. I know we've gone through it really quickly, but you can see, I think, that there is evidence of a lot of different events in our country. We've got a lot of different rocks that spans a lot of different ages, and there's still a huge amount that we don't know. And the key to a lot of these questions is actually sitting within our country. So it's an interesting place to be doing geology. If you have any questions, feel free to hit me up. You've got my email address, or you can contact me through the Moodle forums. Until next lecture, I'll see you later. One last thing. This book is free. Your textbook is American, as all textbooks seem to be these days. It doesn't cover a lot on the geology of Australia. However, there is a free ebook. You can download it from here. It's called Shaping a Nation, The Geology of Australia. A lot of the figures that I've used today have come from that book. It's a really good book. It's written in a really good way. So I would suggest downloading that and reading through it. You don't have to read through the whole thing, but there is just a really good introduction to the geology of Australia in there. So read through that when you get the chance. All right, if you have any questions, you know how to find me. I'll talk to you guys next time.